Today's topic is on statics. We're going to look at two situations where the sum of all forces of the problem are equal to zero. The sum of all forces for some object is equal to zero. And so that means there's not going to be any accelerations, and also they're not going to be moving. This is opposed to the topic of dynamics, in which there is accelerations. So we're just going to jump straight into an example. And I want you to imagine that you have two walls that are fixed surfaces. So in other words, they don't move themselves. If you push against them, they will not move. And we indicate that by drawing the walls and drawing these little lines here to represent that that's a fixed surface. We have a mass that is once again static. It's not moving, it's not accelerating, and it's being held in place by two ropes, which I'll call rope 1 and rope 2, which essentially have tension in the ropes. So you can think of it as a tension force 1 and tension force 2. For today, we're going to call those just F1 and F2, just to make it simple. So the mass is suspended here, it's not moving. Rope 1 is horizontal, and rope 2 makes this angle with the surface up here, theta. The mass is 17 kilograms, and theta is 34 degrees. And quite simply, we just want to figure out how much tension force is in the first rope and also in the second rope. And you might think of, how do we solve this type of problem? We typically start with a free body diagram. So here's the mass. It has gravitational force mg, and the two other forces on it. There is a force in this direction, which we will call F2, and the angle theta. If you think about it, these are alternating interior angles. This is angle theta as well, right? These are parallel lines, so um, that's how we draw it over here. And we have a tension force going off horizontally. That wasn't great. Let's make the line here. And we'll call this tension force F1. Okay, and that is static. It's not accelerating. All the forces are balanced. Now, as we do, we have the free body diagram, and that's correct, but we want to have a more functional diagram, in which case we're going to take this force 2 and create components, a horizontal component and a vertical component. So if you look at force 2, it's kind of pulling the mass up and to the right. And so we're going to have two components pulling up and to the right. This one will be called F2 sine theta, and this one is F2 cosine theta. And we'll put the actual forces, the other forces that are still on there. And this one is F1. I should make mg of equal length to F2 sine theta. Something like that. And of course, there's no acceleration. So at this point, we look here at this free body diagram, and we just have to note that F1 is of equal magnitude to F2 cosine theta. That will ensure there's no horizontal accelerations. And mg is equal to F2 sine theta, and because there is no vertical accelerations. So I'm just going to jump to making two statements. Mg is equal to F2 sine theta, and F1 is equal to F2 cosine theta. So I've kind of skipped what we normally do here. We say F equals ma, there's no acceleration. So we say, for example, F1 minus F2 cosine theta is equal to 0, and that would be our next step there. So I kind of just skipped those steps. Okay, let's see what we know and what we don't know. We know M, we know G, we don't know F2, and we do know the angle. So we could actually figure out F2 right away. We don't know F1, we don't know F2, and all we know is the angle over here. So we can't solve the right equation for F1, but we can actually solve for F2. But I'm going to use a method of substitution. I want to find F1 first. I want to find F1 first. And so if we create an expression for F2 and plug that into this equation in terms of mg and sine theta, we can solve F1 first. So that's what we will do. So just going to rewrite this as mg over sine theta. Okay. And all I did was divide by sine theta, and I kind of flipped it for my convenience. We're going to substitute that in. So F1 is equal to mg. This would be cosine theta over sine theta, which is equivalent to a few things. This is also equal to mg times the cotangent of theta. This is also equivalent to F1 equals mg over tangent theta. And yeah, I think that's good. So I don't know, I kind of like this one. Kind of like this one here. So I'm going to go ahead and solve it this way. Um, we have tangent in our calculator, so we're going to use this one. The mass is 17, so mg is 170, and then it's tangent of 34 degrees. One 170 over tangent 34 degrees. Cool, we get F1 is equal to 252 newtons. Okay. You could have also just plugged in theta into that equation. I just use this one because it's simpler. And if you're wondering where we got these two expressions from, well, tangent of theta is equal to sine theta over cosine theta. Of course, we have cosine over sine, so that means that this would be equal to 1 over tangent theta is cosine over sine theta. That's why the tangent is on the bottom. And of course, this is also equal to cotangent of theta. Cotangent of theta there. Keep going. Let's find F2. We have an expression for it. This is just mg 170 over sine theta, which is 34. Which is 304 newtons. So that was a rather easy one. Again, our strategy is just making equations and doing substitutions. And the fact that it's static, that the sum of all the forces equals 0, means that there are 0 accelerations vertically, there are 0 accelerations horizontally, and that makes it very easy. Cool. Is there anything else I need to say here? I don't think so. So let's keep going. Let's do a little bit harder, problem that's a little bit harder. And what we have here is a fixed surface up at top. You know, the surface up here at the top. there are two strings attached to that surface, um, string number 1 and string number 2. This is angle theta 1 and this is angle theta 2, different angles. And those two strings meet here where it's connected to another string, string 3, that is holding mass m, a block of mass m, at the very bottom. And the mass is 13 kilograms. Theta 1 and theta 2 are 66 and 24 degrees respectively. And our questions are simple. Let's figure out the tension force in the first rope and the tension force in the second rope. We don't care about the tension in the third rope, which we could actually talk about right now. If we make a free body diagram for the mass, which I'm going to erase this, by the way, so you can write this if you want, but whoops, I deleted the whole thing. If we create a free body diagram for the mass, we have mg is pulling the mass downward, and we have a tension force, which I'll call F3, is pulling up on there. Now, with this alone, we can't solve the problem. We can't figure out F1 and F2 if we're creating a free body diagram of the mass. But there is something useful here. We do know that there are no accelerations, and so mg, or I should say F3, is equal to mg in magnitude, right? So the sum of all forces is 0. So mg minus F3 equals 0, and so therefore mg is equal to F3. So although this doesn't help us solve the problem, it does let us know that mg is equal to F3, but you can kind of tell that just by looking at it. So how do we solve something like this? Well, the trick is we're going to do a free body diagram. We're going to make a free body diagram of this location, of this point. So you need to imagine that we're looking at the forces at this location. So I'll do that here. Here's our point. Oops. We have tension force F3, which is equal to mg, by the way. It is not mg, but it is equal to mg. We have a tension force F2. Let me try to get these angles right. It's a little bit long. This is F2. Because of alternating interior angles, this is also theta 2. And then we have a force up here, F1. So once again, I'm calling my tension forces F1, F2, and F3 instead of FT1, FT2, FT3. It's just a little bit quicker. And alternating interior angles, this is theta 1. We have to be careful with these subscripts. We need to make sure that we include theta 1 and theta 2 in our equations, that we're not just writing theta because they're different angles. Cool. This is the free body diagram. And let's not forget that the sum of all forces is equal to 0. There's no accelerations. Now that's great. We're going to draw a functional diagram, like a functional free body diagram, something that we can actually use. And so we need to take F2, we have this angle, we need to make components, but we don't want to do them on the free body diagram. We want to do them over here. So this would be F2 cosine of theta 2, right? F2 cosine of theta 2. We'd have a vertical component, F2 sine of theta 2. Let's make F1 into components. We have a horizontal component. Should be equal length with this one. That is called f1 cosine of theta 1, and we should have a vertical component, and purposefully make this a different length than f2 sine theta 2. It's not important which one's longer, just that we know that they are different lengths. If we draw them the same length, then it would sort of imply that they're equal, but we don't know that, and they're not. So make it a different length, and we'll call it f1. This is sine theta 1. And let's not forget mg. F3, which is equal to mg. And it's with this diagram over here that we can start to set up our equations. And I'm going to write them over here because I have space. Let's do the horizontal because it's just easier. We can see that f1 cosine theta is equal to f2 cosine theta. They have to be equal, otherwise there would be an acceleration. Let's do it like this. Let's not write that. Let's just write f1 cosine theta is equal to f2 cosine. That's theta 1, this is theta 2. We have to include the subscripts. Okay. Now let's do our vertical force and components here. F1 sine theta 1 will be added with F2 sine theta 2. And that is equal with, now I could say F3, but I'm going to say it's equal to mg because we're actually going to be solving now, and mg is just more useful. That would be 130 when we get to that point. So I'll just say, first of all, there's many ways of solving this problem. There's a faster way than what I'm showing you here. And when we're done with this, I would challenge you to try to figure that out. But what we're going to do here is our same method where we write two equations, and we're going to get stuck because we don't know F1, we don't know F2, we don't know F1 here, and we don't know F2 there. So we're going to have to do a substitution of one equation into the other to solve this one. Of one expression, I'm sorry, into the other equation. That's what I meant to say. So let's do this. F1, and it's cosine of theta 1. That's cosine of 66. Don't know F2, but this is cosine of 24. Over here we have F1 sine of 66 plus F2 sine of 24 equals, I believe that's 130. And those are all the things, all the numbers we know right now. Remember that cosine 66, cosine and sines, they're just, when you put in the angle, they're just numbers. So cosine of 66, I'm going to type this in the calculator, is just 0.4067. We use 4 significant digits, significant figures. 4067 F1 equals, now I need cosine of 24, 0.9135 F2. We'll continue. Sine 66 is 0.9135 F1. And sine 24 is 0.4067 F2 equals 130. Now these equations alone, they're separate, you can't solve them, but let's try to get one. Let's try to say something like F1 equals, so we're going to divide both sides by the 0.406. I get 2.246 F2, right? I just divided the 0.4067 on both sides. I have a nice expression here. We will put in this, we will substitute here, that's 0.9135, 2.246 F2, 0.4067 F2. And now we're just kind of cleaning up the numbers, we're just simplifying everything. This is 2.052 times F2 plus 0.4067 F2 is 130. 2.052 plus 0.4067. 2.459. Is equal to 130. And now we will divide. We'll call this 52.9 newtons is equal to F2. No, I should have written that the other way. F2 is equal to 52.9 newtons. If we substitute that back into this equation over here, we get F1 equals to 2.246 times 52.9 newtons. I get 118.9. I'm sorry, 118.8 newtons, which we can just say is 119. Okay. That is the force in, that's the tension force 1 and tension force 2. Like I said, there's another method of solving for this. Hey, if you're watching this video, I'll give you a hint. And the idea is, let's go back. Let's go back one. Here we made this very simple by putting all our forces into two dimensions here, a vertical and a horizontal dimension, so that we have expressions where they can cancel. Expressions where F1 equals F2 cosine theta, for example. So here, my suggestion to you, or my hint to you is, can we get this mg, this F3 force, can we break it up into a component that goes this way, opposite of F2, and can we make a component that goes in this direction, opposite of F1? And I will leave that to you to see if you can figure that out.